Hello, welcome to today's video. Today we are looking at the double angle identities, specifically the proof of them, but also knowing why they're useful, because that's a common thing students get stuck on. They know they exist, but they don't know when they should or shouldn't be using them. So let's kick things off. The first one we're going to look at is sine 2x, and basically the place where these identities come from is by looking back at the compound angle formula. Because if you look at the compound angle formula, of course those are identities for things like sine of a plus b, but if instead of having that sine of a plus b is sine of a cos of b plus sine of b cos of a, if instead of looking at sine of a plus b, we instead decide to look at sine of x plus x, of course we'll realise that x plus x is 2x, but if we then see what impact that has on the right hand side of the identity, we can see we've got sine of x, cos of x, and then plus sine of x, cos of x. And so therefore that means we've got two lots of sine x, cos x. So this is the double angle identity for sine of, sine of 2x. Sine 2x is equal to 2 sine x cos x. So there you go. That's the first of the double angle identities. The second one comes from doing the exact same thing with cos of a plus b. Cos of a plus b, according to the formula booklet, is equal to cos of a, cos of b, minus sine of a, sine of b, and then therefore if we're instead of looking at that, we're looking at x plus x, well again of course that will give us the identity for cos of 2x, but what's happening on the right hand side? Well, we're going to end up with a cos x times by a cos of x minus a sine of x times by a sine of x, and therefore that can simplify to cos squared x minus sine squared x. Nice. Okay, so that is the identity or double angle identity of cos 2x, except there's actually more than one double angle identity for cos 2x. Because we've got the cos squared and the sine squared in there, we can start to use our other identities we know from first year, namely sine squared x plus cos squared x equals 1, to help us rewrite this in some alternative forms. So an alternative way you can write this is you could choose to replace the cos squared with 1 minus sine squared. If you do that, then you're going to end up with 1 minus sine squared minus sine squared of x, and therefore that can then simplify to 1 minus 2 sine squared x. So that's one alternative identity for cos 2x. But there is another alternative, and that goes we get to that from, instead of replacing the cos squared x in terms of sine squared x, we can choose to replace the sine squared x in terms of cos squared x. In other words, the other way around. So doing that, we'll have cos 2x, and then we'll have the cos squared x, and now we're going to replace the sine squared x with 1 minus cos squared x. However, make good use of brackets because the sine squared x was being subtracted before, so its replacement has to be subtracted as well. And if we do that, we'll end up with cos squared x minus 1 plus cos squared x, because we've got the minus minus situation going on, which leads to 2 cos squared x minus 1. And then onto the double angle identity for tan 2x. And again, I think you've probably got the idea by now. It's simply a case of looking at the compound angle formula for tan of a plus b, in other words, the addition angle formula, those sometimes are called if you're only looking at the one with the plus in. And therefore, from the form booklet, that's tan of a plus tan of b all over 1 minus tan of a tan of b. Worth convenient time for me to remind you of being careful whether you're picking the plus or minus in each position in these formulas, depending on whether you pick the plus or minus on the left. But it's more detailed than that. If you pick the plus on the top, that means you're going to pick the symbol that's on top everywhere on the right hand side, and it's because on the bottom it's a minus plus, the minus is on the top, so therefore that's why you pick the minus sign. Anyway, if we are making the a and the b both x, yes, once again, that's going to lead to tan of 2x, but on the right-hand side, we're going to end up with a tan of x plus a tan of x all over 1 minus tan of x, and that then simplifies because at the top we have a tan x plus a tan x, and that means we've got two lots of tan x in total on the top, and meanwhile on the bottom a tan x times by a tan x is tan squared of x. Sorry, my t's look a bit like pluses. So therefore, there you go. There's the double angle identity for tan 2x. So in summary, so far, the identities are, as you can see on your screen. However, a warning. These are not in the formula booklet, and therefore you do need to remember these off by heart. That might seem like a bit of a arduous task because there's five identities written here because of the three different ones for cos 2x. If you're going to make any time-saving efficiencies, then prioritize above all the others, these ones as the ones you absolutely 100% must know off by heart, because the tan 2x, although it's a really good idea you do remember off by heart, compared to the other ones it appears less often, whereas the sin 2x and cos 2x double angle identities appear so much that it is really important to know off by heart, because although we know I've shown you how to derive them, it's not just about being able to find the identity, it's about being able to recognize it, being able to realize you see it, like for instance, a 2 sine x cos x appearing in something and going, ooh, wait a minute, that is sine of 2x. Getting familiar and knowing these things is important, and that will only happen if you know them off by heart. Okay, so that's what they are, but how am I meant to know when I should be using them? Well, we will be looking at a video, in a future video, some specific examples of us, having situations where these things can be used, but just the rough idea, just a general rule, is you're looking for whether in your trig equation or your trig identity that you're trying to prove or anything like that, are the things inside the trig functions matching? If they're not, then that's a situation when you might want to use, well, not only double angle identities, but also compound angle formulas. It's the same idea, because these identities are all for the purpose of being able to convert what's inside the trig function. Whereas if all the trig functions have the same thing inside, then you have no reason to use these identities, because, hey, we've got other ways of being able to deal with what's inside the trig identity once we've dealt with the trig function. But then the issue is a lot of our other identities are only focused on what's what the trig function itself is, and therefore also having the same matching thing inside. Anyway, so therefore that was a bit of a rambly way of saying, look, here's a couple of examples. For instance, if you had sine 2x minus cos of x equals 0. This is an equation to solve. We're not actually going to solve it now, but this is a situation where we would want to use double angle identities, because there's a 2x inside one thing, there's an x inside the other. Those two things are not matching. And so therefore, use double angle identities to help us. Cool. So there we go, very simple rule there. Whereas if we had to solve, I don't know, let's say sine 2x equals cos 2x, in this case, they are matching. And so therefore, there is no reason to use double angle identities, because we don't need to. We can deal with this equation just by realizing sine 2x over cos 2x is tan 2x. So yeah, do be aware of that. Don't unnecessarily just every time you see a 2x just go, oh right, let's use double angle identities all the time, because sometimes you might be overcomplicating the problem when it can actually be solved without doing that. Cool. Right then, so that is double angle identities. As I said, future video we'll actually look at more specific examples of using them and, completing a full question rather than just giving you a sort of beginning bit of knowing when they shouldn't be used. So do watch that video when that comes out. Lovely. See you in that next video.